Hello, my name's Clayton Bly. This presentation will detail the progress made on my individual project report, which entails the design and implementation of a steering angle and road speed control system for a prototype autonomous car. The aim of the project is to formulate and refine a control algorithm which is able to navigate a test vehicle between coordinate waypoints, using information about the car's position and heading relative to the geographic coordinate system. The objectives are as follows. First, to conduct a literature review to investigate the current research landscape which is relevant to the project. Second, to research the hardware requirements along with the underpinning scientific principles that must be understood to complete the project. After this, hardware will be selected based on the newly acquired information. Third, to design and construct a circuit and test vehicle. Fourth, conceptualize the control algorithm, then write a program which encapsulates the algorithm using the C++ programming language. The fifth objective is to test and refine the algorithm using a series of increasingly challenging waypoint reaching missions. Now, to date, objectives 1 to 4 have been completed in their entirety. Objective 5 is still in progress. The car is currently slightly unstable in that it oscillates along the line it should be following. Additionally, there are some bugs that need to be fixed before the code is or the algorithm is fully refined. This slide details the hardware that was selected after objectives 1 and 2 had been met. To orchestrate the control system, a microcontroller is required. Its role is to take measurements from sensors, perform mathematical calculations, and output control signals to actuators. The TNT 4.0 was chosen for this project as it has a very high processor clock speed and a large memory availability, which allows for complex programs to be stored and executed. For macro position measurement, the global positioning system was chosen as it's really the only option for this application. The accuracy of generic GPS is limited to around 2 meters. However, real-time kinematics, or RTK, can bring this down to around 1 centimeter. The configuration of RTK is displayed on the right, where you have a base station and a rover module. The base station sends RTK corrections to the rover, which incorporates said corrections into its location solution, giving the 1 centimeter positional accuracy. Not all GPS receiver modules support RTK. The U-Block's ZF9P does, however, and was selected for this project because it's cheap and has good library availability through SparkFun. To measure the car's heading relative to the geographic coordinate system, a magnetometer is required. It measures the magnetic field strength in X, Y, and Z directions. These three can be used to find the absolute heading of the vehicle. The MPU 9250 was chosen due to its low price and, again, library availability through SparkFun. For the testing platform, the optimal car would replicate the dynamics of a typical road vehicle. So have rear-wheel drive, a differential, and front-wheel steering, and of course fit within the budget constraints. The Funtech Furio was chosen as it has front-wheel steering, which is actuated by a servo motor mounted at the front. It's circled on the right there. And a DC motor at the back, which can be controlled using a H-bridge. The Funtech Furio also has a wide array of mounting holes in the center, which will be useful for mounting control electronics later on. So the configuration of a H-bridge is shown on the top right. H-bridges allow for bidirectional motor control of speed and direction control. The BTS 7960B was chosen as it has a very high current throughput ability and is unlikely to burn out in testing. For data acquisition, an SD card was chosen. It's necessary to record data about the control inputs, outputs, position and heading, etc., to assist in algorithm refinement. And the SD card was chosen as it's very simple to take the SD card out of the car and put it into a computer and manipulate the data. The first step in meeting Objective 3 was to construct the circuit. A diagram is shown on the right there of the relevant components. All of the connections were made on a sheet of stripboard for speed and ease of fixing mistakes and changing configuration options. So the circled SDA and SCL are the data and clock lines of the I2C communication bus, which was used to interface the GPS and the MPU 9250 with the teensy. A serial port UART connects the NRF24 module with the GPS, and it feeds in the RTK corrections, which are sent from another ZF9P module, which acts as the base station and sends out RTK corrections. Orange is circled and indicates the PWM signal lines. 4 are used for the H-bridge speed and direction control, and 1 goes to the servo motor and controls steering angle. The second stage in meeting the third objective was the mechanical construction, which involved mounting the control electronics to the Funtech Furio test vehicle. CAD models were constructed for 3D printing using measurements made of the car mounting hole spacings and the measurements of the stripboard hole placements as well. So once these parts had been printed, the boards were assembled. The second board is mounted with a separation to ensure that the magnetometer readings aren't interfered with by the currents flowing in the motor or in the stripboard. The construction is fairly sturdy and, as you can see in the video, is fairly tidy. The H-bridge is mounted between the motor and the control electronics. The first step towards meeting Objective 4 was to conceptualize the control system. The nature of the project calls for a multiple input, multiple output system in which the inputs are the car's position and heading, and the outputs are its steering angle and the motor speed. To organize the code, a state machine approach was used, where the two master states are the autonomous and manual modes. Switching between these two modes is affected by channel 8 on the radio transmitter. So in one position, the car will be in autonomous mode, in the other position it's in manual mode. In manual mode, the throttle control is the right stick y-axis and the steering angle is the right stick x-axis. So in the manual mode, the car is driven around the desired course, and channel 6 here is activated at junctions and turning points, at which point the car saves its current position as a coordinate waypoint to be reached later when channel 8 is switched into autonomous mode. So the code flow is as follows. First, sensor readings are taken. Then the PPM channels from the transmitter previously pictured are read and stored in memory as global variables. Then the mode is checked. If the mode is autonomous, the perpendicular distance and bearing errors are calculated. Then the outputs from the two PID controllers are summed. And thirdly, the outputs are written to the throttle and steering control variables. If the mode is manual, the receiver channels shown previously are written directly to the throttle and steering control variables. Lastly, the control variables are written to the H-bridge, which controls the motor, and the servo motor, which controls the steering angle. In the last slide, I mentioned two errors. Number one was the bearing error, and number two was the perpendicular distance error. So in order to ensure that the car follows the line joining the last waypoint with the next waypoint, the so-called desired path, both of these errors are relevant. Error one is fairly simple to calculate. It's just the car's heading subtracted from the heading towards the next waypoint. And ideally this should be 0. The car should be facing towards the next waypoint in order to reach it. And the second error is the perpendicular distance between the car's current position and the straight line which joins the last waypoint with the next waypoint. So this is a little more complex to find, but involves determination of a straight line function which joins the last waypoint with the next waypoint, then finding the equation of a line which is perpendicular to that line, and finding the distance along that perpendicular line between the car's position and the desired path. Again, this error should be 0. So this slide shows the block diagram representation of the steering angle control system which was implemented. Sensor readings come in from the magnetometer and the GPS and are processed through the red blocks to formulate two error signals which are passed through individual PID controllers which will be tuned individually. The outputs of these two controllers are summed with a 90-degree constant. This is in place so that when the outputs of the two controllers is 0, the steering angle is 90 degrees, which correlates to the car traveling directly forwards. The output of this summing junction is output to the steering angle. So anti-wind-up is incorporated into both PID controllers and prevents the integral term from increasing uncontrollably whilst the steering angle is at a maximum. Additionally, a low-pass first-order filter attenuates the derivative noise. Raw magnetometer readings are notoriously noisy and require filtering to be usable. If raw readings were used in a control system, the control actions made would undoubtedly be unpredictable. So an infinite impulse response filter was used to filter the magnetometer readings instead of a finite impulse response filter because they give sharper and faster responses, according to Siemens. The only downside to infinite impulse response filters is that they require floating point operations to be made, where finite impulse response filters only use integers. Thankfully, the Teensy 4.0 has a very fast floating point unit, which allows it to deal with floating point operations in the same way that a standard microcontroller would deal with integer math operations. So the filter was kept as a first order filter just to ensure stability and to simplify the filter design and tuning. So the Laplace transform of a first order filter is shown there, where it's given by k, the gain, multiplied by 1 divided by tau s plus 1, where tau is the time constant of the filter. In the discrete time domain, for this example, the heading is equal to the last heading at t minus 1 multiplied by the filter weighting summed with the new measurement, all divided by x plus 1. And that was the form that was implemented in code. So on the right hand side we can see the effect of changing the filter weighting. When the filter weighting is high at x equals 50, the response time is very high. The filter takes a long time to reach a new value with a set point change. However, the filter works very well, I suppose you could say, in that the line is very smooth. You know, the output or the filtered heading is unaffected by noise. As a side note, each x-axis division is equal to 10 seconds. So you can see that when x equals 50, the filter takes around 15 seconds to respond. As x decreases, the time constant also decreases and the response time decreases. You can see when x equals 10, the response time is around 2 seconds or so with a set point change. X equals 10 was chosen as the final value for the filter weighting as it was deemed to give the optimal response. For road speed control, the algorithm is a great deal simpler than for steering angle control and works based on the distance to the next waypoint. This distance is calculated using a Pythagoras equation, squaring the latitude distance and the longitudinal distance, and finding the square root of that to find the distance to the next waypoint. And when this distance is greater than 3 meters, the car travels at a constant speed. As soon as the car goes within 3 meters of the next waypoint, a proportional controller kicks in and gradually reduces the speed of the car to around half of its original speed. This is just to ensure that the car doesn't overshoot the next waypoint too much, and additionally there is a minimum speed limit imposed so that the car does not come to a stop. So this slide demonstrates that the manual section of the code is fully complete and operational. You can see the steering angle and bidirectional control of the motor speed has been effectively implemented. So I suppose the first thing I can think of is that nobody else in the literature has documented calculating the perpendicular distance from the car or the autonomous rover to the line which joins the last waypoint and the next waypoint. This was my own idea, and as far as I can tell, it's novel. The second thing would be that, as far as I could tell, nobody else has implemented RTK for this application. RTK will allow this car to be steered through obstacle courses that cars which don't use RTK would not be able to navigate accurately or reliably. Also, the filter design for filtering the magnetometer readings is completely novel and was created specifically for this project by me. So the way that most other projects that I can find affect steering angle control is through bang-bang control, which leads to oscillations, so the steering angle will never settle at 0. Whereas the way that mine works, it has a PID controller processing the error heading. So if that error heading is 0, i.e. if the car is pointing directly at the next waypoint, then the steering angle will be 90, i.e. the car just goes forwards. Additionally, the way that I've chosen to input coordinate waypoints to be reached in the autonomous mode is different to how other people do it. They tend to program the coordinates directly in code, whereas the way that I've done it is the car is driven around in manual mode, and along the way the coordinates are saved as waypoints to then be reached later when the car gets put into autonomous mode. I feel that this method is just quicker and easier to set up and access, and it makes more sense to me. Also, the method that most other people have used to input control actions to their autonomous vehicles is through Bluetooth or even a Wi-Fi connection. I've utilized pulse position modulation channels which are controlled via an RC, a standard off-the-shelf RC controller, which meant it was very quick and easy to get the project off the ground and implement the manual control mode, or it simplified it somewhat when compared with using Bluetooth or Wi-Fi control. It also gives finer control over the position and speed, or steering angle and speed, because this RC controller was designed to control cars or planes, what have you. So one way that I know that the work I'm presenting is correct is that my supervisor has confirmed that I'm along the right lines. If I've made any jumps in my logic, I've asked him whether or not they're justified and make sense. Some of the work kind of speaks for itself in that it demonstrates that it's correct, such as the first order filtering of magnetometer readings. The result is a much cleaner signal, so I suppose you could call that correct. Additionally, before starting the project, I read a book called Applied Digital Control by J.R. Lay. I took a lot of inspiration from the book, and it helped me, or guided me along the process of designing this control system. Well, the first thing that comes to mind when I think of ways that I could follow up on this project and things I could do next is model predictive control. Model predictive control would allow for the route between the waypoints to be optimized. So if I was going for speed, for example, if the car was to be entered into an autonomous race, then optimizing this route would be really necessary and important. Additionally, using a Kalman filter to filter the results of the GPS or the output of the GPS could negate the need for RTK if the Kalman filter's system model is sufficiently accurate. Then positional accuracy can be attained to within 5 centimeters or so. The Kalman filter would use information from the accelerometer and gyroscope in order to achieve this. In terms of what I'd do differently, I think I would manage my time better towards the start of the project. I wasn't particularly efficient with my time towards the start of the semester, and that meant I had to make up for the lost time later on.